I'm Anil Kumar, and this video is for my subscribers who are going back to university. They have been out of touch with mathematics, and now this will kind of give them some review of old concepts so that they could take up courses like calculus in first year university. So in this particular video, we'll talk about approximating area under the curve, and we'll take up trapezoids, which can help us to approximate area under the curve. From here, we'll build up the concept of Riemann sum for approximation, and then definite integrals and so on. So let's look into the trapezoid first. So it's a figure which is kind of like this. Two opposite sides, I should say, it has one pair of parallel sides, right? That is kind of important for this quadrilaterals. Four-sided figure with a pair of parallel sides, right? So normally we just label them A and B. So let's say this is A and this is B. These two sides of the trapezoid are parallel. Now, height of this trapezoid is h. So height is actually the distance between the parallel sides, right? So it is perpendicular or the shortest distance between the parallel sides. Area of trapezoid is equals to half sum of these two parallel sides, say A plus B, times height. So that's the area. Now, it has a very simple proof which we can give you right here in a minute. Consider, let me extend this a bit, right? So consider this to be trapezoid to be combination of two triangles. Let me just cut it across, right? So if I divide it like this, we get two triangles, and let me call these triangles as A1 and A2, let's say. Okay, so let's say this area is A1, this area is A2. Now what is the area of a triangle? Area of a triangle, let me write down here, okay, A1. Area of the triangle is half base. So for this triangle, base is B times height. So that's very clear, right? So that's A1. How about A2? A2 is also a triangle whose base is A. So we say A2 is half. Base is A times height. Now what is the height of this one? Well, that could be tricky. What you can do is you can kind of extend this side. You know, this is parallel to this one, and that's the height, right? So say the height is same as the height which we define. These two sides are equal, correct? So it is the same height. So that results into writing area of the second triangle as half A times H, right? So the total area is combination of these two. So we say area of trapezoid is A1 plus A2. So if you add these up, so these are same things, right? So we can take half H common, right? Half H, and we are left with half, I'll write H later, A plus B, or B plus A, or A plus B, and this is height H. Do you see that? So BH, AH, I took H common and wrote A plus B, right? So that is the formula, so easy to derive. So that's the area of trapezoid. Now how does it help to find area under a curve? We'll see that part. So we have already done this part, which is basic formula. Now let's look into area under a curve. So I'll begin with a very simple example. Let's take a straight line, right, as a curve. Okay, so let's say we have a straight line here. So let me sketch a straight line. Okay, so this is a straight line going in both the direction. Okay, now let's give a equation to this straight line. So let's say since this has some y-intercept, we'll call this straight line as y equals to, let's say this is 1 and slope is also 1. Let's keep it simple. So it is x plus 1. So that is my straight line. Okay. Now, what I'm interested in finding is area between the straight line and this x-axis, right? So this is my x-axis, that's the y-axis. So area, let us say this is 1, and let's say this point, okay. So what I'm interested in finding is area between x-axis and this line, and I'm interested in all this area, right? So that's the area which I'm interested in finding, right? So it's also a curve, straight line is a curve, right? Okay, no doubts about it. Let's say this point is at x equals to 1, and we'll keep this as x equals to 3, and we want to find what is the area of this shaded portion. Now you can see this is a trapezoid as we are talking about. The only thing is height in this case, it has been like rotated 90 degrees, right? So instead of having two parallel lines which are horizontal, we have vertical parallel lines, right? So the area of this curve is equal to area of the trapezoid, which is half base, which is in this case height, right? So let's write this as let me write first height in this case, which is this one, right? This is my height, okay? And then we want to find sum of the two sides. So these are my two sides. Do you see that? So this side is how much? This is the value of y when x is 1. Do you see? So I'll write this as f of 1. Do you see that concept for function notation? And how much is this height? This height is value of this function when x is 3. Do you see that? Right. So these are the heights. Do you understand? This distance and that distance. So we'll add them up. That is to say, f of 1 plus f of 3, right? So that is a plus b, sum of these two lengths. Is it okay? So these are the parallel sides. I hope the concept is clear. So in this particular case, we can just substitute the values, find the answer. We have area of this curve as half. Height, we are calling this as the height, which is 3 minus 1, right? 3 minus 1, that is the height. And f of 1 means substitute 1 here. So if I write 1 here, what do I get? I get 1 plus 1 as 2, right? Okay, so let me just fill up these things here so it becomes easier. F of 1 will be equals to 1 plus 1, 1 plus 1, which is 2. Do you get it? So I'm substituting this value 2 here. Okay, plus what is f of 3, right? F of 3 will be, I'll substitute 3 here. So let me write here, f of 3 will be equals to 3 plus 1, 3 plus 1, which is 4. So I'll write 4 here. Do you get the point, right? So the idea is that this length is 4 units, f of 3, and this length is f of 1, which is 2 units, right? And the area of this trapezoid is exactly equal to what we've written here. Now we can calculate the values, which is half of that is 2, and this is 6, and that gives us a half and 2 cancel, 6, right? Unit square, we don't know what units are, so let's put unit square. So this is how you could find area under the curve using the concept of trapezoid. So what you see here is perfect. It is exact area, right? Exactly, it matches with the area we're talking about, and that really happens because we are working with a function which is linear, right? So in case of linear function, calculating area is not a big deal, right? So it, as expected, we got perfect result. Good job. Now we'll take some curved surfaces, and I think we'll jump over to some really complicated curve, which is very useful. So what I will do here is I'll take a curve which is sine curve. So okay, so sine curve is, you know, kind of like this, right? So I'll just make a part of it, okay, since we'll run out of space. We'll do something else here. So that's a part of sine curve. Let me write this function as y equals to sine x, right? So that makes it clear. And we'll find area under a boundary condition. We'll make a trapezoid, right? So let's say this is the peak, which normally will be at pi by 2, right? And then let's take a point here, okay, which is, let's say, pi by 6. You know, sine pi by 6 is half, that's why I've taken this value. And sine pi by 2 is 1, right? Sine pi by 2 is 1, right? Now, if I construct a trapezoid here, then what happens? See, this is a curve, so I'm approximating. This is my one side of trapezoid joining these 2 points. And these are my parallel sides. And this is my x-axis. Do you see that? So now I'm trying to find area under the curve sine x between the interval pi by 6 and pi by 2. That is the concept, right? Now, when you get to integrals, you're going to write this in a complicated way, which will be kind of like this. Let me introduce you. So that's the integral sign, sum of areas from pi by 6 to pi by 2 for this function, which is sine x, and we'll say dx. That is how you're going to write very soon, right? So we are approaching this place now. This was also in the same fashion, right? This also I could have written as area equals to integral of the function x plus 1 dx, and the limit was from 1 to 3, right? And we got our answer as 6 by using approximate methods, by approximating using trapezoid. Exactly same method we are going to adopt here. We are getting into this complication now, right? But we'll soon be there. That's the whole idea, right? Okay. So one big trapezoid is here to find the area of this curve. Now how do we find it? Well, again, apply the same formula, right? Same formula, a equals to half sum of parallel sides times the height. Height will be the distance between these 2 parallel sides, okay? So we say area equals to half. Sum of these 2 sides is, as you can see, half and 1. This is half, and that is 1 unit. So it is half plus 1 times distance between these 2, which is pi by 2 minus pi by 6. Let me write pi by 2 minus pi by 6. No difficulty, right? So pi by 2 minus pi by 6 is the difference, right? This. And these 2 are these sides, half and 1. Is that okay? But it gives you area of that trapezoid, which is lesser than the actual. Do you see the actual curve is going like this? So at this time, the curve is concave down. I'm introducing you to a few terms so that the coming chapter is easier for you. Okay, let's calculate this area. Half and half plus this is 3 by 2, okay? And this is, oh, I have to put plus, right? We have to add these sides. So 3 pi by 6, 3 plus 1, 4, so it is 4 pi by 6. Is that okay? And that gives you, we can calculate this. This 2 and 2 cancels with 4, 3 cancels with 2, and so we get pi by 2. This is in radius, right? So if you have to write, you know, decimal values, pi is approximately 3.14. So it is 3.14 divided by 2, which is 1.57, right? So we have an area of 1.57 units square, okay? So that's the result, pi by 2, right? So pi is 3.14 for the time being, irrational number, okay? Now, so what you see here is that you can get approximate value of area under the curve using trapezoids. Now what you need to appreciate here is that I could have made many trapezoids, right? I could have made many trapezoids, and if I would have done with many small trapezoids, I would have got a very accurate result, right? So that is what we are going to learn soon. But what you understand here is 2 things. One, we can use a trapezoid to approximate area. Most important from here is that this area is going to be lesser than the actual area, right? So what we get here is, since you can see it's concave down, so we say when the curve is concave down, so it's like a cup put downwards, right? So when the curve is concave down, then approximation is lower. So it is less, you can see, right? It is less than that amount. So this is very important to understand. Well, let me take a function now which is concave up and see whether the approximation is higher in that case or not, right? So another example, just to show that in concave up, things could be different, right? Okay, so concave up is a structure which is like 1 over x. Let me sketch one here, okay. Okay, so we have a curve here, and this is for y equals to 1 over x. Now that's the curve for 1 over x, and you can say it is concave up, right? Is concave up, correct? Concave up. So here, if I need to approximate and find the area, then what should happen? I guess we'll get higher area using trapezoid. Let's see. Okay, so let's say this is the point which is one point we are considering, and let me just make a trapezoid kind of like this, okay, and let this be the second point. Fine, so we have to find what this height is and what this, I should say, the side lengths, okay. So it has been rotated 90 degrees, okay, fine. These are your parallel sides, so these are your A's and B's. Fine, A's and B's. So for this curve, let me take these points, simple calculations, right? I'll take this as 1. So 1 over 1 is 1, right? 1 over 1. Let's take this as 2. So 1 over 2 is half. Okay. So we have this trapezoid again, trying to find area under the curve, I should say, area between the curve and the x-axis this time. Okay, so this is my area which I'm looking into, right? I want under the curve. I want this. But what am I getting? I'm getting something extra. Do you see that? That extra portion? Yes. So one thing we are very clear about, that in this particular case, when we have concave up, approximation is higher, right? Since we are, you can see, extra area is being considered. Is it okay? So that's one part. Now let's find the area using this formula, right? Such a good formula, right? So in this case, you'll see that A is 1 for us and B is half for us, and height is equals to 2 minus 1. 2 minus 1, which is 1, and therefore area is equals to half A plus B, which is 1 plus half, times height, which is 1. Simple, right? Simple. So this is half 3 by 2 times 1, and that gives us 3 by 4. Let me write unit square, right, since we didn't scale it up. At this point, let me conclude by saying that this simple area of trapezoid can really help us to approximate very well area under the curves. We have taken extremely simple examples to illustrate. If you have a linear function, then the approximation is exact. If you have concave down, then the approximation is on the lower side, and if you have concave up function's curve, then the approximation is on the higher side. Now I've taken big trapezoids. If you could have broken down into smaller trapezoids, that is to say, this distance between parallel lines was reduced. In that case, we would have got fairly accurate value. So that is to be appreciated. So in the coming videos, we will see how to get very accurate results using these concepts. And I'm Anil Kumar. You can always share and subscribe to my videos. Feel free to post questions. Thank you and all the best.